Hello everyone. So today I'm going to be continuing my studying on the Linux kernel. So today I'm going to be focusing on programs and processes, error handling, and user identification, and depending on how quickly that goes, might move on to signals and the remainder of chapter 1. Guess we'll go right in. Sorry. So to begin, the book says that a program is just an executable file. On the disk. A process is an instance of a program. Sometimes operatings also call this a task, like in Windows, but in Unix generally they're called processes. In Unix, every process has a unique process ID, which is a unique identifier for the process. PID. So if you run a program, e.g. hashtag include appu.h int main void printf hello world from PID long decimal \n long get PID. And exit 0. Basically, this get PID function is included in appu.h, and what it does is it just gets the PID of the process, which you can also import manually, but I guess you don't need to for brevity. Now if you run it, ./a.out, you get hello world from PID some number 1092. And this will change for any process. By default in Linux, you have on the order of, I believe, millions, if not either hundreds of thousands or millions of process IDs before it loops back and reuses them. So this will just increment gradually as you run the program. Or if you just keep your operating system online for a long time, it'll just keep increasing as random things in the background start and stop. Now we'll move on to process control. The three main system calls are fork, exec, and wait PID. Wait PID. Now, quick note, this is actually like 6 different kinds, but essentially we're just gonna call it exec. We'll probably mainly use execve, but there are different versions of exec that you can use for different cases. So, an example of running a program. So you want it to make a shell. Basic shell. You want to include pu.h, include sys/wait.h, and int main void. We're gonna initialize some variables. Car buff max line, which is from here. PID T PID and int status. Now we're just going to printf $, which typically you get when you see in the kernel. You would expect something like a $sign at the start, and that's how you would know to run the command or type something in. So while fget s buff max line std in not equals null. So while we keep getting a valid input to the shell, we will keep doing the while loop. Now if buff len buff -1 is the new line character, we set that to be null. That's null. Um, what's the best way to do this? I'll rewrite the while get s buff max line std in now equals null if buff then buff -1 dash buff then buff -1 equals 0. So that's just rewriting the same thing we had before. Now what we want to do is we want to fork the process. PID equals fork. Less than 0. Sys fork error. Else if PID equals 0, exec lp buff car star 0 return code didn't execute. S buff exit 127. Otherwise, you're in the parent. If PID, so wait, PID, and status 0 less than 0, sys wait, PID error, print f $, and exit 0. Sorry about that. So what's happening in this loop? Basically, what's happening is first get input from user, or this could be a script or something. Replace end /n with null. And this is just for the exec lp function we have here to work correctly. Next, what happens is we run fork. And what fork does is it creates 2 copies of the process. So let's say we have a process here. PID is 312. PID 312. Still the same process. 2. 1, 2. And PID is some other number. 416. So this makes an exact copy of what we have, and the only difference is the PID. Now the value that fork returns the value depending on which copy of the process you are in. Actually, probably a good idea to clarify. Fork creates a copy of a process. If you are in the parent, it returns the PID of the child. If you are in the child, it returns 0 because the child does not yet have a child of its own. You could run a child within it, but we won't worry about that. That would be the same thing. So we run fork. From our process that has PID equals 312. 2. And we get the parent. And a child. Four, 1, 6. And here PID 416 and PID equals 0. Now if we recall the code we had written, it checks that if this returns some value less than 0, then something went wrong. Maybe there's too many processes and we ran out of IDs. Maybe there's not enough RAM, or maybe some other issue. Doesn't matter what the issue is. If there is an issue, it won't return a positive number, and that means we have to deal with the error. Otherwise, if the PID is 0, in that case we are in the child. Run if child. And then it would exit. Otherwise, you're running it as if the parent. Run if parent. If that doesn't run, then we have a PID of the child, and that's working fine. So an important part to do is the wait PID here. Wait PID basically says, oh, this process is running, but so let's say the CPU is running process of the parent. It's not strictly guaranteed that the parent and the child will be running at different times. Maybe when you fork, it will start with the parent, or maybe you'll fork and it'll start running with the child. And what we basically want is, in a basic shell, is when you run a command, the command runs and then once it's done, we can run something else. Now you can add an ampersand afterwards and have it run in the background, but for now, that's not what we want. We just want, if we run a program, we run the program, and we don't want to run anything else until after it's done. What waitPID ensures is while the child is still active, the parent process just waits around and doesn't do anything. It just says, oh, thanks for letting me run, but I don't actually need to run right now, because this guy still hasn't finished his task. Continue on to the next process. And then subsequently, when child is finished, then waitPID will say, oh, thanks, that guy's finished. Now we can run another command. So waitPID waits for child to finish. Now this runs execv, or execlb in this case. And what execlp does is basically it clears the entire memory of the process that it is in, so the child process, with PID equals 416, and replaces it with a new program. So the child process runs execlp, which replaces the memory of itself with a new program. So while it's forked, it has the same code, so it's still running the code we saw earlier. But once it's forked, we want it to run something else because we typed in the terminal, please run ls or some other command, and execv changes it so that it starts running a different command. Basically copy pastes the binary code into the memory and deletes the old memory. And once execlp is done, it basically just kills the process, and that's returned from waitPID. Parent process runs waitPID, which waits for the child process to complete and returns the child processes termination status. I usually want it to return 0 because that indicates that it ran successfully, but otherwise can happen, and that's okay. So the main problem with execlp is that it only runs the command and nothing else. You can't input any parameters, which is mainly why in most cases you'd probably opt to use execve or some other case of an exec, but in this case it explains what we want well enough. So example of it running. So for example, you could have in a terminal /a.out after compiling it, and you get this. You could run ls, and you would have a list of the programs. So my shell .c a.out. Can also run anything else. Date. I'll give you the 8th of May. That's a dot, whatever time. 2012. Or anything else. Now some things here won't actually work if you go cd dot slash or something else. That won't work because cd has to be interpreted by the shell, and also arguments don't work. And set it up, and cd must be processed by the shell. So we'll have a quick note on threads. Usually, on most Unix operating systems, and in most cases, one thread equals one process. Usually. However, you can also have process use multiple threads, which is more complicated to write code for, but can be done if you need a high performance program. In Unix, processes also have thread IDs, which are specific to the process. So in other processes, the thread IDs would be different. And that's basically all you need to know about threads so far. So for now, we'll continue on to error handling. So when an error happens, it is the job of the kernel to respond to those errors. sometimes errors can be trivial, other times not so trivial, but no matter what, it's the kernel's job to handle those errors. So when a process has an error, sometimes a negative value integer is returned. In Unix, there is a variable called kernel, which is kind of a global variable which holds the value of the type of error it had. So for example, when you run open a file or something, it can return a value such as I'm not sure what the values are, but it can return numbers such as permission, error, or could not find, or something else. The error numbers are defined in no.h. Now you can also have it be run multi-threaded. So if you want to do it historically, Erno is defined as extern int Erno historically, or for multiple threads. You would define it extern int star underscore no underscore location void, or hashtag define no star underscore no location. The main two rules for Erno are one, that the value of Erno is never changed by a routine if there's no error. No error. no, not changed. And 2, no is never set to 0. So if you run a function and so what you can do is you can check erno before running a function, maybe it's equal to 12, then you can run a function, it has no errors, and checking after, it should still be 12, unless some background process changes erno. Now, to help with erno, with erno, we can use some functions in C to understand the error. So one such thing is to use hashtag include string.h and car star stir error int num. And basically this function returns a string for any given erno. So what you can do is you can also use the p-error function. Can also use p-error to produce error message. So that'll be hashtag include stdio.h and void the error const car star message. So basically what this would do is print message colon space, which I will denote like that, and corresponding error message. Depends on error. So that would be something like str error of error no. Now an example program for this is hashtag include apu.h hashtag include no.h int main std error e s percentage s backslash n str error e s. And basically this is constant defined in the kernel. Oh, sorry, looks like I made a mistake here. Should be int main int argc car star argv f print f and this content. Next we can set error now to be a specific error, which is no int, and we can do p error argv 0 and exit 0. Now running this, we get ./a.out get first you get s permission denied and ./a.out no such file or directory. So basically this is str error of no int because we set error no to be no int, and this is str error of access, and no int is also another constant defined in the kernel. Now what about error recovery? So basically, what it says in the book is in errno.h has two kinds of errors. Fatal and non-fatal. Basically, for fatal errors, we just end program and print error. And for this, can be dealt with. Manually or otherwise. So non-fatal errors include things like not having enough storage temporarily or something else. So examples: E again in file, E no buffs, E and no look, E no SPC, E would block, E no met sometimes, and E fuzzy sometimes. And E and TR sometimes. Typically, what you do is you delay and try again later. This is usually determined by the developer. Now we'll start our next section, which is identification. Is section 1.8. So first things first is the user ID. And basically, this is a number or an integer, I should say, is associated with a virtual user. And this is determined and by the sysadmin. And usually this is unique. UID 0 is given to the root / super user. And basically this guy is very cool. Can't do anything. Bypasses any privileges. Now group ID. This is also assigned by the sysadmin. Usually these are used to collect groups together. This allows sharing files and other resources. And you can change the permissions so that anyone in your group can read files or anyone can modify them. Similar to maybe how like you can invite people to a Google Docs and anyone can edit it, or you can make it so only other people can see it, or you could completely block off them as well if you wanted to. Now, YIDs. Well, mainly because checking IDs is much easier. Then strings. The numbers can usually be kept in a byte or two, whereas for strings you have long strings of bytes, and that's a lot more effort to check and probably also more liable to errors. This also allows people to change their username if they want, but still have the same ID and be able to access things much more easily. So typically on Linux, if you do something like g include apu.h int main void print f uid equals $d gid equals $d /n get uid get gid exit 0. Now if you do something like /a.out, usually you get something like uid equals 1000 GID equals 1000. Now if you do this with sudo do ./a.out, you get something like UID equals 0, GID equals 0. You can also have supplementary IDs. Can also have supplementary IDs. Regroup IDs. Which will also be stored in /etc/group. /group. And user ID will be in /etc/pass/wd. Okay, so that's basically everything I wanted to cover for today. I guess tomorrow I'll cover signals, time values, and syscalls. And that's end of chapter 1. So yeah, that's basically everything I covered. We learned about programs, how they are run, how processes are instances of a program. Every process has its own unique PID. Processes are mainly controlled using fork, exec, and wait PID. We took an example of a simple shell with a simple while loop. We learned how you take a user input, modify it slightly, and then you run fork to create a copy of the same process of the shell. In the child process, you execute the program, which replaces the memory of the shell to the program you wish to run. Otherwise, it runs. Once this is finished executing, it goes to the parent. The parent continues running and finishes up. So next we look at threads. Learned that processes can use multiple threads if they need more performance. Thread IDs are specific to each process. We learned that with error handling, each different type of error has a unique errno defined in errno.h. We learned that errno is only ever changed whenever there's an error, and it's never set to 0. The main reason for that is maybe you could have the child of a child have an error, and you want it to propagate back up so you can tell if there's been a new error. We also learned that you can convert the error number to a string, which is some nice functions in C that you can use. We took an example of it printing it out, the error, not just giving us a string. We also looked at some different kinds of error. So you can have fatal errors, which always terminate the program, and you can have non-fatal errors, such as if you have no memory at the moment, you can come back again and try it again later. And then lastly, we looked at identification. We learned that user IDs are unique, usually unique to every user's, and are a preferred way compared to using strings to finding if a user owns a file, as IDs are much easier to store. We also learned that every person has a group ID, and sometimes they can have multiple in the /etc/group file. And we looked at an example of printing UID. And yeah, okay. Thanks for listening.